should lecture myself. And last but not least, just that. Ready, steady, go. Hope I have everything done right. Good, excellent. Here we go again. Now, where are we in the beautiful life of this course? We went from basic linear control initially to understand a little bit of basic linear control, including some very simple concepts of stability. And then we essentially departed towards nonlinear control. And for that, we started with coordinate transformations, direct kinematics, and inverse kinematics, which are the kinematics, or the kind of the geometry of the robot considerations. What we want to do today now is actually the final two topics which we need for nonlinear control. We need to understand how to create nonlinear equations of motions for robots as we normally have them. And the big topic in this area is actually what is called rigid body dynamic methods, or rigid body dynamic systems. Since all the robots which we deal with at this moment are essentially stiff links which are connected, or basically links which essentially don't bend, at least in all what we care about. And they're connected by motors and joints in some form and create motion the way we want. Now, the topic of rigid body dynamics is essentially how to model robots which fall into this realm of systems. And it has multiple ways how you can approach it. And what we're going to do today is essentially we will go into the first way of doing it is Lagrange equations. And the beauty about Lagrange is it is way more intuitive and easier to understand and to derive than what we do the next time, which is Newton-Euler. Newton-Euler is way more efficient because it's a recursive algorithm which can be computed literally in linear time relative to the number of degrees of freedom you have. Lagrange's method can be done in this way too, but you have to make some major extra efforts to get it going. But it's so much easier to understand that it's worthwhile starting with it. It's the most small system, that's the method of choice. Newton-Euler is the method of choice if you have really complicated systems. Okay. And we'll just crunch to that, have a whole bunch of slides, and then we use some illustrations from the book as well to get going on this. So these two topics today and the next time are potentially having a little bit more equations than some of you like. And it's all about physics, sorry. But that's what robots are about. They're all about physics. So we just go through that. I'm not really, basically, what do I expect from you guys to understand? What I would like you to know is essentially that there are methods how to derive physics equations or equations of motion in a principled way. That's one thing. I want you to know a little bit what choices you may have. So for instance, Lagrange and Newton-Euler. I would like you to understand at least in principle the basics behind those methods. Obviously, you will not know them by heart, and nobody wants to know that stuff by heart. It's annoying. But you need to understand really how's the recipe, how can I create equations of motions, how do they look like, how are they structured, and what we're going to do later on is actually we're going to exploit the structure of these equations to derive nonlinear controllers. That actually then becomes important. How this is computed on a real computer in the end is there's software programs which can create equations of motions for you if you provide a kinematic descriptions, not unlike what we've been discussing before. That means you know homogeneous transformation matrices from every degree of freedom to every degree of freedom to every degree of freedom, you know, the link lengths. So kind of the stuff which goes in the David-Hartenberg formulation. This is why we're building really little steps on top of each other. And all of these things always are needed in the next step until we finally come to nonlinear control, and then we can actually control more complicated robots. Good, let's see how this works. Most likely I'm going to run out of time, so I have to try to make this sufficiently swift. Okay, super simple. Lagrange equations are so easy to work with that's not even funny. And we don't derive them. It's actually not too terrible to derive them. What is important is that it's an energy consideration. we basically look at the kinetic and the potential energy of a robot. And that is T is the kinetic energy, U is the potential energy, and L is called the Lagrangian, which basically is the kinetic energy minus the potential energy. Okay, and this is like a complete energy of the system. There's a beautiful thing on this world, you know, you have energy, and if somehow the energy changes, someone has to put some work into the system and push it. And that is essentially what is exploited here in Lagrange's equation. If you look at this is now two kind of, so first comes a partial differentiation of L with respect to the joint velocities, and then the time derivative of that, minus the partial differentiation of L with respect to the joint angles or degrees of freedom in general, then this has to equal, and this is for every degree of freedom I, this has to equal the forces and torques, or forces or torques, depending if it's a linear actuator or a revolute actuator of the system at this point. That is the main thing. And we don't derive this, but the intuition is simple. You know, change of energy at every degree of freedom of the entire system also has to be attributed to someone pushing it, putting torques or forces into the system. Otherwise, the energy would not change. It's conservation of energy. Good. And we'll see, we'll exercise it. You will see how this works. It's actually very straightforward. First of all, when people talk about this, and I mentioned it before, they talk about generalized coordinates. It means any coordinates which can model your robot, but please the minimum number of coordinates. And we basically fooled around how you can basically define a joint angle relative to the world coordinate system or relative to the previous link. But normally you would like to choose something which is the most intuitive. Most of the time we do things relative to the previous link. So this is where the motor sits and pushes. Important is that this entire formulation does not care about which coordinates you choose. Since the energy will not change, you can compute it in whatever way you want. In the end, the total energy can only be total energy. And if it's becoming more in one coordinate system than the other, something
That's, we're back and connected. Perfect. Fine. Good enough. Just gotta make sure that this pointing in the right direction. Okay.
Becomes the sum of all kinetic energies of all links. Okay? And U will become the sum of all potential energies of all links. And now we need to figure out how hard it is to and we skip the motors. So we need to somehow look at how to derive the velocities of our joints. And essentially the consideration which goes in there just checking. There's the world coordinate system. Up here is our friend, the potato body, with its own little coordinate system. And its coordinate system has an offset vector. Let's see that I do some useful notation. So let's call this P. Link I. Why is there an L in there? I have no idea. Ah, that must be, okay, fine. I'll get to that in a second, hopefully. Okay, that's good. This is PI, it's just an offset right now. And okay. And I need, yeah, okay, now I know what the notation is. This here is link I, that's the offset, and we want to look actually at a particular, sorry, make this precise. We want to look at a particular point here, which is PI on the body with distance okay? Link. And this here is the distance of and then we can basically figure out what's the velocity of this point, given that we have this information. This is essentially what this thing should be saying. This the velocity of this point pi is obviously the velocity of the potato body. Okay, so this is right now blasting with a velocity of dot. It's moving with a certain velocity. And if we just look at this point here, then that would be it. If this point, the fat point would coincide with this point, we wouldn't need anything else. But given that this thing is now rotating, no, sorry, omega I, times Ri. Shoot, my notation sucks. Sorry. This here is Ri, distance PLI, and then, okay, fine. I should remember my notation better. PLI, and this here is in the end the velocity of this point. Which is P in the world coordinates. Okay, that's obviously confusing. Try again. So the potato body has this distance, PLI, from the previous coordinate system. It moves with some PLI dot pointing in some direction. It rotates in general with some omega relative to this point. And we're considering a point here, which is Ri offset from the point which we've already modeled. And then we can write the velocity of this point according to this formula, which makes essentially sense. It's translating, it's rotating. The rotational component basically adds an additional velocity to the translational velocity. Good. Fine. A little bumpy, but we got that thing sorted out. And now the question is, how do you get from knowing this? Now, this basically allows us to model the velocity of every point on the robot relative to the previous coordinate systems. And we can always basically run it through coordinate transformations. Down there, we can do everything in world coordinate systems to start out. And that's what we're going to do. So
here the book pages will be useful, hopefully. Let's try. Okay. Old rule, make the window very small. Move it over here. Then make it bigger. And look at this like that. Cool. That's what I want. So that should hopefully now allow me to get through this. Perfect. So we start with the kinetic energy. Say the kinetic energy is the sum of all kinetic energy terms. And here in the book, as I mentioned, he uses the motor kinetic energy as an additional term. So yes, this is now much nicer, and I should have pulled up that plot before rather than fooling around with my notation. So this is now the link here again is our PLI, our distance of the center of mass of the relative to the, say, world coordinate system. This is the point which we care about. It has Ri distance to the center of mass. It is Pi as a point in the world coordinate system. The link moves with a velocity. That's why I use these things. That's why you can recreate them. Now, how is kinetic energy defined in general? So let me just go back to this. And this little guy here is the generic definition of a kinetic energy, in this case of link I. Let's look at this for one tiny moment of time. It is 1/2 an integral discussed. So tell me there's dots missing. There's so many dots everywhere. Good. Okay, we're back online. Hopefully, this does a little bit better now. All right, now, what we're going to do is we keep on using this integral, and we use some additional information which is useful. We want to basically plug in everything in there which we know. One thing we know is actually what the velocity of that little point is. That's what we just wrote down before. So the velocity of this little point, pi dot star, I think I have all the dots on everything, equals PLI, the link velocity, plus omega cross Ri, all with little i's. And because we don't like cross products, since they're ugly to work with from a linear algebra point of view, we'll just replace it with our matrix operator of the cross product. Remember that thing that we talked about this pretty much in lecture 1 or 2, lecture 2. Cross product can always be represented as a Q-symmetric matrix operator. Now we just have normal linear algebra, which we know how to work with. Okay, now, so we can plug this thing in here and multiply it out. I'm not going to do all of this. This is too frustrating for me to do on the whiteboard. It will take too long. We use actually one additional fact which is useful, and that is here the definition of the center of mass, from what I recall. So this here says PLI, which is essentially the center of mass in our world, is 1 over mLi, so the mass of that link. And then we integrate over this entire volume of the link, Li, and we integrate all pi stars. Notice these are not velocities, these are positions. Rho, d, v. Okay? That defines the center of mass of a body. Is this true? Hopefully it says that somewhere. D. Let me check. Yeah, I think. Does he say that? D. Yep, center of mass. It's here. And we have this. Good. Now, what we do is plugging everything together. And so first of all, we plug this thing in here and do a transpose times itself. So not so much fun to do this all the way. What will happen is essentially, let me just punch that as is, because I can do this nicely on a whiteboard. So we have this term, we transpose it, and multiply it with itself. Is no star, sorry. P dot plus S of omega I R I. All right. So now if we multiply it out, which essentially means we multiply this term with this term, we multiply this term with this term, this term with this term, and this term with this term. So we get a total of 4 terms, okay? And then we just try to interpret these terms. That's all we're going to do. So one of them, which is very easy, is essentially PLI dot transpose times PLI. So this is when we multiply this with this. And then there's the other term, the general one, which is if I write, now I do a little bit of linear algebra. So this multiplication transpose becomes equivalent to Ri transpose times S transpose Wi S of Wi Ri. Okay, remember transpose operator reverses the sequence of things. So this is the multiplication of this with this. And then the other part is the cross terms, which have maybe PLI and the SWI and RI in there. Okay. So let's just look at how this comes. So first of all, the simple one is this one. P dot Li, one of the dots missing again, times PLI. This is just, and then if you put it back in the integral of rho dv, This is nothing but the standard translational velocity. Okay? So that's easy. This term here, super easy to interpret. Now, then here comes the mixed term, which he calls the mutual term. So what's happening here? So this basically has PLI transpose times SWRI, and then it has the same one more time, just with the transposes reversed. Now, what did he do here? We have this term 2 times. That's basically where the factor comes in there. Well, I'm not sure how much I should explain that, but I'll just do it a little bit too much most likely. So let me get rid of this. I have a touch of space. And we have P dot Li transpose times S of Wi Ri. This is one version. And then we have the other version, which is Ri transpose S transpose Wi times P Li transpose. And does anybody see that these 2 terms are the same, despite we change the sequence and the transposes? It's a beautiful fact of life. You want to know that? It's really cool. Look at that. It's a number. It's the number 3. Now, what's the number 3 transpose? Well, it's just 3. Isn't it cool? Transpose of a scalar is the scalar itself. That can change. Now, look at this thing. A transpose vector, and here's a, so this is a row vector, this is a column vector. This has to be a scalar. This is just some generalized bilinear form. Remember this beautiful linear algebra nonsense we did initially? So this is just a scalar. And then it's a scalar transposed. So they have to be the same. That's it. Very simple things. Cool. So that's basically why he says we can do that times 2. Now, what does he do now? So if we have PA transpose, he basically says he pulls out the P, okay, the velocity of the link is not changing over the volume. It's a constant. It's nothing which is a function of the volume. So he pulls that out. The rotational velocity, the cross-wire term, does not change as a function where it is on the link. He pulls that out. So you get all these things out. And then he basically says, okay, let's write R, the vector R, I, simply as Pi star minus Pli. Okay, that's fine. That's what the figure said, in case you remember. Just let me move up. Here it is. This is just saying Ri can be expressed with the help of these 2 vectors. Not a big deal. Okay, then if we have this, now we have this integral again. And this PLI term, again, is constant. So the integral can be split into 2 integrals. There's one term we take out. And all what we are left with is an integral, which is, again, well, it's actually nicely here. It's then Pi star integrated over rho dV, which is the definition of the center of mass, which is equivalent to PLI. So basically, the whole idea is that these 2 terms in the end, basically this entire term becomes 0. Complicated, weird, annoying. More explanation, fewer explanation, go home, drink coffee. Coffee is always a good idea in general. Okay, this is basically where he goes back to this. That the definition of the center of mass is this here, and he just basically has here a term which is integrating over the entire mass with just the mass term. All right, you can look at this for a moment, you will figure it out. It really just boils down onto, the main component is this guy here, the definition of the center of mass position. which he uses here and then crosses this term out. Okay, so fine. It gets a little bit annoying, as you notice, but at least you get a feel for it. If you don't fully understand, it's okay. You could stare at that for a little bit longer. So we have the last term we had. So we talked about the translational term. This was our friend. The cross term, actually here, this is our cross term, goes to 0. We got rid of this. So we just have to look now at the last term, which is the square term for the second term. Square term for the second term. Nobody can understand that if you would just listen to me. Fine. This is this thing here, plugged in. So here we have, I wrote it out there, R transpose S, R. Okay? Now, what does he do? He basically uses a little trick. One of the tricks is that S of W times R equals, I think, minus R. Bad. Minus W times S of R. What? What the hell? I'm recording that, right? It's really bad. Remember the cross product. A cross B equals minus B cross A. Cross product can always be written here as S of A or S of B. Now see how this rule comes into being? So very simple. But now we play a little bit linear algebra, and it turns out to be useful. So basically, he reverses this R times S of omega. He makes that omega times S of R. And because he has the terms twice, all the minus signs or whatever, they cancel. They don't matter anymore. So and then he pulls out again out of the integral the stuff which is constant. Omega is constant. Does not change over the volume. So all what we are left here is this thing, which is S transpose R of I, S of R, rho dV. Fine. And nicely, he also writes out for you one more time the definition of S of Ri. This is just the definition of the cross product in linear algebra as a matrix. Just to write it down here one more time. And now you can take this and plug it in and multiply this entire thing out. It's not pretty. Nobody says it's a lot of fun. But what you get is essentially this term here when you multiply things out. So there's a whole bunch of little integrals. And if you stare at these integrals, these are definitions of a moment of inertia in general, of a three-dimensional moment of inertia. There's these moments along the diagonal, which are the main moments, and then there are the kind of cross terms, which are the kind of additional moments. We don't go into this into large detail, but essentially we just derived a moment of inertia definition through this energy consideration. Okay, good. A little bit annoying, but what boils down to, does he write this in the end? He does. In the end, basically, this term here converts to something which includes the moment of inertia that becomes the rotational kinetic energy. So, wait, does he have that? Almost like on the next page. There we go. So we get this. Remember, just double sure that you at least follow me. Oh, here he wrote it up. That's what I've been looking for. So this cross term, integral over it, is nothing but omega I transpose I, the moment of inertia, times omega I. So that's essentially omega I transpose I, that's kind of stupid implementation, times omega I. And we are done. So we basically now showed how from a generic consideration of kinetic energy, we derive a translational kinetic energy and a rotational kinetic energy in grand general. So this is all included in Lagrange properly. And then what he just does here is basically he says, okay, if you care, since it's annoying, the moment of inertia, if you are out on a link in a multi-degree of freedom robot. So now I need a little bit of space again here. So we are and our favorite multi-degree of freedom robot out there, if you express the moment of inertia of this link in world coordinate system, then it becomes configuration dependent. It changes all the time. If you express it in local coordinate systems, if there's an ith coordinate system, for instance, attached to this guy, here, which makes xi, yi, and zi sticking somewhere, then the moment of inertia is actually constant relative to this local coordinate system, and that's kind of convenient. So he basically says, oh, why don't we simply express the inertia in terms of its local inertia? And that is the formula. I'm not going to derive this right now, how to convert a local inertia with a rotation matrix I into world coordinate system. Now the notation gets really annoying. Okay? Oh, gosh. So we have essentially, at this point, I, Li, I. So that is the inertia of link number I expressed in the I coordinate system. This super and subscript at some point become a little bit frustrating. Okay, and this can be transformed with the help of the transform Ri to 0 if we wanted to use our own old notation, and then Ri to 0 transpose into the inertia expressed of Li expressed in the 0, that is in the world coordinate system. And you can do the same thing for an angular velocity. It's obviously clear that you just use the rotation matrix and express it in local coordinate system. So this is the world coordinate system, angular velocity expressed in local coordinate system, or if you want to do it the other way around, you just take the inverse of R, which is just, again, its transpose. Oof. God. In the end, we do all this fun stuff, and we get something which is now much nicer to work with. So we get the kinetic energy as 1/2 of link number 1. Maybe I should make this a little bit bigger even. Okay, better. So kinetic energy, link number 1, is its center of mass velocity times its mass times 1/2. Super simple. And its angular kinetic energy comes from the inertia expressed in local coordinate systems, then the rotation matrix to this coordinate system, and the angular velocity of that link. So it's in some sense just a generalization of what we did for the simple pendulum, but now we have it in its grand beauty. Okay, fine. So let me go back, I think. To the slides at this moment. So we basically talked about this. Now we spent a whole bunch of time on the book, and we basically ended up with this formula. Here is not with I didn't put the rotation matrix in there. Now the question is in the end, then, how hard is to compute all these terms which are in there? That's really what we care about. So currently these are all expressed in world coordinates. Quantities, you can express them in local coordinates. And where do we get everything from? So mass. 1/2 is mass. Well, you hopefully get from some specifications from your robot manufacturer, or if you have to take the link, dismount the entire robot, put it on a scale. Okay, you get a mass. Yeah, I'm not sure whether they can put it back together, but that's a problem we do not address. It's all theory here. Inertia. Hopefully you get it also from some CAD specifications. Now that becomes actually a little bit tricky. Masses are pretty straightforward from computer-aided design. Inertias can be iffy. They don't always reflect all the parts in the system. So the motors can come inside. There might be wires. There might be, if it's a hydraulic robot, it has fluid dynamics inside. These inertias which you get from computer-aided design become so la la correct. But you can get it from computer-aided design. You can also, actually there's experiments, if you have no computer-aided design information, you can do pendulum experiments and basically estimate from the frequency of the pendulum what the moments of inertia are. That is a pain in the rear end, but it's totally doable. It can be actually done much more elegantly by just having a robot holding it and just with a force torque sensor at the wrist and wiggling it around for a few seconds, and the moment of inertia is determined. Okay, so we get this. Usually we get the inertia in local coordinates. Here's the transformation from local coordinates to world coordinates, which we already talked about. And do we have everything here? Rotation, link. We know how to get rotation matrices from our homogeneous transformations. So I think we have everything on this. And last but not least, we need the velocities, p dot of the link and omega I of the link. And the key insight is this is something which we can get from our kinematics knowledge. So let's go. If we go back to a nice robot picture, 1, 2, 3, like this. This is our n effector, for instance. Now we know how to compute the direct kinematics for the n effector. Okay, this was something like x equals f of q. And we talked about this, how we can get this through a chain of homogeneous transformation matrices. Now, the center of mass of every link is just the equivalent of an n effector. So, for instance, the center of mass here sits at this point. The center of mass here sits at this point, at this point. Well, fine. Forget about the gripper. Say this is the point for which you want to do your direct kinematics. And you compute the direct kinematics for this point, which is all the same transformation, homogeneous transformation matrices, except for the last one, the offset vector will be different. It will be shorter than the one to the n effector. So remember our good old friend, homogeneous transformation matrix has R, he has the offset vector, and then it has a friendly amount of zeros and ones. All that changes here is this guy. It has to be a little bit shorter to hit that center of mass. Okay, now that means you can actually compute the Jacobian for this, and you can simply say this Jacobian times the joint velocities, which you somehow have from your robot, give you the link velocity, or the center of mass velocity and angular velocity. So with your previous knowledge, you know how to do that. And now we do the same thing for this point. And for this point, we simply imagine this is a new robot where the stuff on top has been essentially truncated. And this is perfect. So this is very easy to calculate. It's just your Jacobian became a little bit shorter. So our big Jacobian, which originally consists of one row for every link, well, right now I lost one of those columns, sorry. Okay, and I can, of course, now keep this going, and I can compute the velocities of every center of mass and the angular velocity of every center of mass. Oof, perfect. So, same story now. We did the kinetic energy. You see, it's a little bit painful, but it's totally doable. It's like a issue of sitting down, doing it carefully, and getting it right. But do you know how to get things right? It's a very important question in life. How do you get things right? How do you know that what you write on paper or whatever is correct? So you need usually some independent verification, which can be your best friend deriving the same stuff. If both of you come up with the same result, that's usually a good idea. Or you derive one thing on the pencil and paper, or the other second time you do it in Mathematica in case you know how to work with these kind of symbolic math programs. Or find out another second source of verification. Often certain things can be numerically verified. But it's very important. It's so easy to just write something. When you notice that in my little Lagrange example, I already made a sign here. Actually, this one I didn't do intentionally. Sometimes I do it intentionally. You just make these sign errors. There's just nothing you can do about it. It's just, you know, at some point in the night, you just get tired. Cool. Potential energy now, the potential is much simpler. It's just the sum of potential energies of every link is mass of every link, the gravity vector, and the position vector of the center of mass. Piece of cake, the position vector of the center of mass is part of our homogeneous transformation matrices, just as we talked about them. We have them trivially. Okay, and then comes the glorious and last slide of the day. And so after deriving these equations of motions, people did that primarily in the 70s and 80s. It was actually, it's not a very old topic scientifically. And then they did this Lagrange method, and for a big robot, actually, Lagrange become a huge number of equations, really big. And they stared at them. And then at some point, after staring at them for a sufficiently long time, they figured out there's a huge amount of structure in those guys. And the structure is summarized here in this very general formulation, what comes out of every rigid body dynamics formulation. In the end, the equations of motion can be written as B of theta, theta double dot, plus C of theta, theta dot, plus G of theta equals tau. So this is a vector matrix equation. For every degree of freedom, you have one row through these equations, or have one equation, okay? So if you have 10 degrees of freedom, there would be 10 rows. So what does this mean? So there is B of theta, this is our first part, multiplying some acceleration, the acceleration of our degrees of freedom. This thing is actually called the rigid body inertia matrix. Since the terms in there are only inertial terms, they're only about inertias and masses, essentially, and they're only position dependent. They do not depend on velocities or anything else. Now, the next term is called the Coriolis and centripetal matrix, or that's actually a vector in this particular case. It's multiplied out. Some people actually write it as a matrix, which looks like C of theta, theta dot times theta dot. And it's a matrix. There's two different ways to do it. So the physical interpretation is that in there, only these terms which are called centripetal and Coriolis forces. You guys know what these things are, remember? Okay, go back to where do you want to go? Yeah, Magic Mountain will do the job. Whenever you go through a curve, the stuff which basically pushes you into the little seat is your centripetal force. So when you are here and you're rotating, then there's a force which tries to push you out. If you would let loose, or if the wagon would let you loose, you would fly away. So centripetal force, this guy. Coriolis forces are a little bit odd. Many people will not remember, but the experiment for that thing is very simple. So this is now a top-down view of a carousel. It's just a plate, okay? This plate is rotating with omega. And here in the middle, that's you. There's a very big nose. It shows in which direction you're heading. There's a top-down view, and you have now tried to walk in this direction. Okay? Now, what is going to happen while you're walking there? Will it feel like happy day? And just basically, the moment you get off the center, you get the centripetal force, which pushes you outward. But is that all? No. There will be another force, which pushes you actually to the side. It makes you fall over while you're walking outward. And that is the centripetal force. No. Coriolis force. God, I can't confuse myself. Coriolis force. Okay, this is just while you're walking outward, you would actually have to gain velocity while you're getting further and further outward. And that requires an acceleration. If you don't gain this velocity, you would actually have to work on some of a bizarre curved path. Okay, so these are the two forces which are in that C term. G is trivial, it's just gravity forces. And this has to equal all generalized torques. There is some useful knowledge about this. that B has to be a positive definite matrix, so we have some linear algebra knowledge about this thing. We can also look into these equations in more detail, and you would find out that all dynamics parameters, means inertial terms and mass terms and center of mass terms, appear only linearly. What does it mean? Well, they never appear inside of a cosine. There's no cosine of inertia, for instance. And there's also no mass squared. There's also nothing like center of mass in x direction squared or something like that. It only appears in linear form. Never, because it just can easily basically pull it out of the equations if you have a term. And that actually enables something which is really cool. You can do actually parameter estimation. All the inertial parameter estimation, all the initial parameters of the robot can be estimated from data. We'll talk about this at some point a little bit later. Okay, let me try to do one last thing super fast. In case I manage to do that, we have this still here. And all I wanted to do is get my mouse pointer over there. It was just there a second ago. Okay, here we go. Let me do this. And forget about my paging through this at high speed. It's annoying, I know. And you can basically, he just goes through a bunch of examples what equations of motions look like for more complicated systems. So take a two-joint arm, and I think he writes the entire equations of motions at some point, which is here. Let me see. Like this. So the two-joint arm, which we use all the time, creates equations of motions which look like that, which is surprisingly messy. Okay, lots of terms in there, lots of annoyance. So important, he puts all the motor terms in there as well. So you see something with a subscript m that means motor, which you can skip. But you can look at, so here for instance, theta double dot 1, so the acceleration of the first degree of freedom. And you can look at what is it multiplying. It multiplies an inertial term, and ml squared is another inertial term, forget about the motor, another inertial term, m times a distance. So it's all inertial terms. This is exactly why people call this here the rigid body inertia matrix. The terms are only referring to inertia. Then you can analyze the other terms in a similar way. The surprising thing is this becomes, just for 2 degrees of freedom, becomes this big. If I do it for 7 degrees of freedom with Lagrange, it would be like 30, 40 pages of math. Actually, this is not true. If we do it with Lagrange, the naive way, it would be a couple of hundred pages of math. Lagrange is very stupid because it recomputes the same subterms again and again and again and again. And Newton-Euler, which we're going to talk about the next time, will actually avoid that. That's why we need Newton-Euler as the practical algorithms. We use Lagrange as the intuitive algorithms, which is on an energy-based argument, which is much somehow easier to understand, I think, most of the time. Done. Next time will be a little bit more equations, but not much more. A little bit more physics, but it's not so bad. And then we're done with that part. And we only use most of the time this equation from then onwards, assuming that some miracle can actually compute these terms. We'll talk about how to compute them. Thank you.